You know, we usually think of sound as this invisible wave that just fills the air around us. But what if I told you that on the tiniest quantum level, sound is actually made of individual particles? And even wilder, what if we're now learning how to control those particles one by one with some truly world-changing results?
All right, so let's just jump right in. I want you to picture a microchip. But instead of pushing electrons through it, what if we could build one that processes information using tiny packets of sound? It's a pretty startling question, but it's exactly what scientists are working on.
And this isn't just science fiction. Researchers are building these incredible, intricate structures right now, things that can literally trap and guide sound waves with pinpoint accuracy. We're not just talking about making things louder or quieter anymore. This is about completely rewriting the rulebook for how we can use sound itself.
To really get this, we have to meet the star of the show, the phonon. So you've heard of a photon, right? That's a single particle of light. Well, a phonon is the exact same idea, but for sound. It is the smallest possible packet of vibrational energy in a material. And learning to control it, well, that changes everything.
So today, we're going to dive into two really cutting-edge frontiers where mastering these phonons is leading to some amazing breakthroughs. First up, quantum circuits built for sound. And after that, we're going to get into something even more mind-bending, time crystals.
So let's start with frontier number one, quantum sound circuits. The idea of creating circuits that run on these little particles of sound.
But you might be asking, wait, why, right? I mean, we already use photons, light particles, for things like quantum communication. Why try to bring sound into the mix for something as complex as a quantum computer? What's the point? Well, the big reason, it turns out, comes down to size. Photons are fantastic, but at the microwave frequencies used in a lot of quantum systems, their wavelength is actually kind of long. Phonons, on the other hand, have wavelengths that are 5 orders of magnitude shorter. That's 100,000 times smaller, which means you can build devices for them that are way, way more compact.
And that brings us to the key piece of tech here, the phononic integrated circuit, or PIC. Honestly, the easiest way to think about it is just as an acoustic microchip. It's a little device specifically built to trap and guide individual phonons through these tiny channels.
If you were to look inside one of these things, you'd see these incredibly small structures. They're basically waveguides, and they're designed to act like a microscopic highway system just for sound particles, making sure they go exactly where you want them to.
The real trick, though, the big hurdle, has always been getting these circuits to actually talk to a qubit. You know, the basic building block of a quantum computer. The goal was to build this perfect connection, a way for the qubit to reliably spit out and then later absorb a single phonon on command.
And guess what? They did it. Take a look at this graph. The orange line shows a qubit just on its own. It takes a pretty long time to release its energy. But that blue line, that's what happens when it's connected to the phonic circuit. Boom. It rapidly fires off a single phonon into the chip. That's the link they were searching for.
And how much faster are we talking? About 19 times faster. This boost is known as the Purcell factor. And getting a high number like this means the circuit is doing an amazing job at getting that qubit to emit a phonon exactly when it's supposed to. This is a huge first step toward building a real, scalable quantum computer based on sound.
Okay, now let's switch gears to our second frontier. And I'll warn you, this is where things start to get really weird. Forget about circuits for a minute. Let's talk about a bizarre new state of matter called a time crystal. So, what on earth is a time crystal? Well, in a normal crystal, like a diamond or a snowflake, the atoms are arranged in a pattern that repeats in space. A time crystal, on the other hand, has properties that are uniform in space, but they change. They oscillate in a repeating pattern over time. The material itself is kind of pulsing over and over again.
So that leads to a pretty wild question, doesn't it? We know what happens when sound hits a normal, static wall. But what happens when a sound wave tries to pass through a material whose very nature is constantly shifting back and forth in time?
The answer is just nuts. It gets louder. Look at the graph here. The transmittance, which is how much sound gets through, goes way above 100%. Now, that should be impossible. It means the sound wave is actually getting amplified as it passes through, basically sucking energy out of the time crystal's weird pulsing.
Okay, so how is this even possible? It's because this periodic pulsing creates something called a momentum gap. And inside this gap, sound can't just travel normally. It splits into two modes.
one that just fizzles out and dies, and another one that grows exponentially, stealing energy from the oscillating material as it goes.
And it gets even crazier if you stick the sound source inside the time crystal. The scientists measured that same emission boost we talked about before, that Purcell factor, and found it could shoot up to over 100. The time crystal basically becomes this incredibly powerful, built-in amplifier for sound.
So, let's pull these two incredible frontiers together. On one side, we've got these tiny quantum circuits that give us precise control over single phonons. On the other, we've got these bizarre time crystals that can amplify sound exponentially. What does it all add up to?
So why does all this matter? Well, it's huge. This work opens up totally new paths to building quantum computers that are smaller and more scalable. It lets us create devices we've never had before, like super-efficient acoustic amplifiers or even sound lasers. It's basically a powerful new toolbox for engineering with sound, and it pushes the absolute boundaries of physics.
And look, don't just take my word for it. As the researchers themselves put it, these devices are elementary building blocks. What they built here is the very foundation for a whole new way of processing information, using the quantum mechanics of sound itself.
Think about it. We've had the electronic age, which gave us computers. We're living in the photonic age, which gives us the internet. But when you look at foundational work like this, you just have to wonder, are we watching the very beginning of the next big thing? Are we about to enter the phononic age?